It is the morning of September 1st, 1859. In a small private observatory outside London, a wealthy amateur astronomer named Richard Carrington is doing what he does most mornings, sketching sunspots. He has spent years doing this, methodically, precisely, mapping the surface of the sun with the kind of obsessive patience that only a man of independent means and unlimited time can afford. Then something happens that has never been recorded in human history. Two brilliant white flares erupt from the surface of the sun, blinding, intense, gone within 5 minutes. Carrington is so startled he calls for a witness, but by the time anyone arrives, the light has vanished. He makes a note of what he saw, files it away, and moves on with his day. 17 hours later, the world changes. The largest geomagnetic storm in recorded history tears through Earth's magnetic field. Auroras explode across the sky in colors so vivid and so widespread that people as far south as Cuba and Hawaii look up and see the night sky burning. In the Rocky Mountains, gold miners wake up at 1 in the morning, convinced it is dawn, and begin making breakfast. And across the entire planet, the most advanced communications network in the world catches fire. This is the Carrington Event. And if it happened today, experts say it would be the most expensive disaster in human history. Richard Christopher Carrington was born in 1826 in London. His father owned a brewery and left him financially comfortable enough to pursue science as a passion rather than a profession. He built his own private observatory in Surrey and spent the better part of a decade doing something almost no one else was doing at the time: systematically observing and recording sunspot activity. This was considered a niche pursuit. The sun was well understood as a star, but its surface activity and any potential connection to events on Earth was largely unexplored territory. Carrington changed that. On the morning of September 1st, as he sat sketching the sunspot clusters he had been tracking for months, he witnessed what we now know was the first solar flare ever observed and recorded by a human being. A sudden, violent eruption of energy from the sun's surface, releasing in an instant what scientists would later calculate to be the equivalent of 10 billion atomic bombs. He had no idea what he was looking at. Nobody did. The concept of a solar flare didn't exist yet. Carrington simply noted what he saw, observed that something extraordinary had occurred, and made the crucial intellectual leap that this event on the sun might be connected to disturbances on Earth. He was right, and that insight, made in a small observatory in Surrey on an otherwise ordinary morning, would become one of the most important observations in the history of science. So, what exactly was the Carrington Event, and how did it work? The sun is not a static object. Its surface is a constantly churning mass of plasma and magnetic fields, and periodically those magnetic fields become twisted and unstable. When they snap and realign, they release enormous bursts of energy. What Carrington witnessed was one of these releases, a solar flare of extraordinary magnitude. But the flare itself was only the beginning. Accompanying it was something called a coronal mass ejection. A coronal mass ejection is essentially a cloud of magnetized plasma, billions of tons of charged particles hurled away from the sun at tremendous speed. Most coronal mass ejections take 2 to 4 days to reach Earth. The one that followed Carrington's flare made the journey in just 17.5 hours. It was traveling at roughly 1,800 miles per second. For context, a typical coronal mass ejection travels at around 300 miles per second. This one was 6 times faster. When it hit Earth's magnetic field, it didn't just interact with it, it overwhelmed it. Earth's magnetic field acts as a shield, deflecting most solar radiation away from the planet. But a coronal mass ejection of sufficient power can compress and distort that shield, forcing charged particles deep into the atmosphere where they interact with gases to produce auroras. The Carrington Event was so powerful that those auroras appeared not just near the poles where they are normally seen, but across the entire planet. In Boston, a newspaper reported the light was bright enough to read by at midnight. In Colombia, at the equator, the sky turned crimson. People who had never seen an aurora in their lives and lived in places where auroras are never seen looked up and saw the sky on fire. It was, by every measure, the most intense geomagnetic storm in the instrumental record. The auroras were spectacular. But the real story of the Carrington Event is what happened to the technology. In 1859, the most advanced communication network on Earth was the telegraph. Thousands of miles of copper wire stretched across North America and Europe, connecting cities and countries in what was then called the Victorian Internet. It was the backbone of commerce, news, and government communication. When the geomagnetic storm hit, it induced massive electrical currents directly into those telegraph wires. The effects were immediate and bizarre. Telegraph operators across the United States and Europe reported that their equipment had stopped working. Some reported sparks shooting from their machines. Some reported receiving electric shocks. In several documented cases, paper near the equipment caught fire. But perhaps the strangest phenomenon of all was this. Some telegraph operators, having disconnected their batteries to protect their equipment, discovered that their machines were still working. The storm itself was generating enough electrical current in the lines to power the telegraph system without any external source. In Boston, 2 telegraph operators conducted an experiment. They disconnected all batteries entirely and attempted to send messages using only the current induced by the storm. They communicated successfully for 2 hours. The storm was so powerful, it had effectively replaced the power grid. Consider what this means. In 1859, the most complex electrical infrastructure on Earth was telegraph wire. The Carrington Event overwhelmed it completely. It generated more power in those copper lines than the batteries designed to run them. Now ask yourself what would happen if the same storm hit the electrical infrastructure of the 21st century. This is the part of the Carrington Event story that keeps scientists and government officials awake at night. In 1859, when the storm hit, humanity had telegraph wires and not much else in terms of electrical infrastructure. The damage was dramatic but contained. No one died. The telegraph system was repaired within days. Today, the picture is almost incomprehensibly different. Modern society runs on electricity, not just for convenience, but for survival. Hospitals, water treatment plants, food supply chains, banking systems, communications networks, emergency services, all of it dependent on a continuous, uninterrupted flow of electrical power. And all of it, every single element of it, is vulnerable to a Carrington-level geomagnetic storm. Here is how it would unfold. A solar flare of Carrington magnitude would first bathe Earth in a wave of X-ray radiation, arriving at the speed of light, roughly 8 minutes after the eruption. This alone would disrupt radio communications and damage satellites. The coronal mass ejection would follow, arriving anywhere between 17 hours and a few days later, depending on its speed. When it hit, it would induce massive electrical currents in any long conductor on Earth's surface. That means power lines, pipelines, railway tracks. The same phenomenon that powered telegraph wires in 1859, but now running through a global network of electrical infrastructure that carries millions of times more power. Those induced currents would overload transformers. And here is where the true catastrophe begins. High voltage transformers are the critical nodes of the modern power grid. They are also among the most difficult pieces of industrial equipment to manufacture and replace. A single large transformer can weigh over 400 tons, costs millions of dollars, and takes between 1 and 3 years to build and install. The United States alone has approximately 2,000 of them. A Carrington-level storm could destroy hundreds of them simultaneously across multiple continents within hours. The National Academy of Sciences estimated that such an event could leave up to 130 million Americans without power. Not for days, not for weeks, potentially for years. Because the transformers that would need to be replaced cannot be rapidly manufactured or stockpiled, the economic cost has been estimated at over $2 trillion for North America alone. Recovery time, according to some experts, could be anywhere from 4 to 10 years. 4 to 10 years without reliable electrical power in a society that requires it to keep people alive. Now here is the detail that puts all of this in terrifying context. This nearly happened 12 years ago. On July 23, 2012, a coronal mass ejection of Carrington magnitude erupted from the Sun. Scientists who have since analyzed the data describe it as the most powerful solar storm in at least 150 years, possibly the most powerful since 1859 itself. It missed Earth by 9 days, 9 days earlier in Earth's orbit, and it would have made a direct hit. NASA physicist Daniel Baker, who led the team that studied the event, said this afterward: "If it had hit, we would still be picking up the pieces." The storm traveled through Earth's orbit at over 2,000 kilometers per second, more than 4 times faster than a typical coronal mass ejection. It would have had almost no warning time. Satellites would have failed, GPS systems would have gone dark, and vast sections of the global power grid would have collapsed. The reason almost no one knows about this is simple: it missed. There was nothing to report, no damage, no disruption. The storm tore through the exact point in Earth's orbit where our planet had been 9 days earlier, and then continued into deep space. A 9-day difference between business as usual and a global catastrophe, and the odds of it happening again are not reassuring. One study calculated the probability of a Carrington-level storm hitting Earth in any given 10-year period at around 12%. Another estimate from NOAA puts the frequency at roughly once every 500 years. Scientists disagree on the exact figure, but they agree on the core point. It is not a matter of if, it is a matter of when. The Carrington Event is often discussed as a distant historical curiosity, something that happened to a simpler world with simpler technology. But there is a more recent event that proves the threat is real, present, and ongoing. On March 13, 1989, a solar storm far smaller than the Carrington Event hit Earth. Within 90 seconds of the storm reaching Quebec's power grid, the entire province lost electricity. 6 million people lost power. The blackout lasted 9 hours. The storm that caused it was measured at roughly 1/3 the intensity of the Carrington Event. Hydro-Quebec's power grid collapsed so quickly that engineers had no time to respond. The currents induced by the storm tripped circuit breakers across the network faster than any human operator could intervene. Transformer damage was significant. The financial cost ran into hundreds of millions of dollars, and this was a moderate storm, not an extreme one, not a Carrington-level event. A storm roughly 1/3 as powerful caused a 9-hour provincial blackout affecting 6 million people and cost hundreds of millions of dollars in 1989. Scale that up to Carrington magnitude. Apply it not to the power grid of one Canadian province, but to the interconnected electrical infrastructure of North America, Europe, and beyond. And ask what 9 hours becomes when the transformers can't be replaced in days or weeks. The honest answer to whether we are prepared is no, not fully. Efforts are underway. NASA and NOAA operate solar monitoring systems that can detect coronal mass ejections and provide some warning time, typically between 15 minutes and a few days, depending on the storm's speed. The faster the storm, the less warning you get. A Carrington speed event would give us less than a day. Some power utilities have taken steps to harden their infrastructure. The United States passed the SHIELD Act in recognition of the threat. Some countries have developed protocols for manually switching off sections of the power grid ahead of a storm to reduce damage. But the scale of the preparation lags significantly behind the scale of the risk. High-voltage transformers remain largely unprotected. Manufacturing capacity to replace damaged ones remains limited. International coordination on grid protection is incomplete. The scientific community is largely in agreement on what needs to happen. Harden the transformers, build stockpiles of spare parts, improve early warning systems, develop rapid response protocols. These are not technologically impossible tasks. They are expensive and politically difficult ones. The Carrington Event is the clearest possible demonstration that the sun can reach into our infrastructure and disable it. It did it in 1859 to a world of copper wire and chemical batteries. In 2012, it nearly did it to a world of satellites, digital networks, and interconnected power grids. The question that scientists keep asking and that governments keep deferring is a simple one. When the next Carrington event arrives, will we be ready? Based on current preparations, the answer is probably not. On the morning of September 1st, 1859, Richard Carrington watched two white flares erupt from the surface of the sun and disappear within 5 minutes. He noted what he saw. He made the connection between what he observed in space and what happened on Earth 17 hours later. And in doing so, he gave us 165 years of warning. The sun has the power to reach across 93 million miles of space and collapse the electrical infrastructure that modern civilization depends on for survival. We know this. We have known it since 1859. We came within 9 days of experiencing it in 2012. The Carrington event was not a once-in-history freak occurrence. It was a demonstration, a preview of what a sufficiently powerful solar storm can do. The next one is out there. The sun is still churning. The magnetic fields are still twisting and snapping. The question has never been whether another storm of this magnitude will occur. The question is whether it finds us ready. That is the Carrington event. If you want to go deeper on the events and phenomena that science still struggles to explain, subscribe to Horizon Archives. We'll be back next week.